So far in the switching theory and logic design, we have studied different type of number systems, conversion between one number system to the another number system, like decimal, binary, hexadecimal, octal. Then we move to different types of codes, your BCD code, 8421, 84 minus 2 minus 1, XS3 code, gray code, and conversion between gray code to the binary code and binary code to the gray code. Now we move to the switching part of this particular subject. We start with the binary logic. So, what binary logic is, how to convert, how to manipulate binary logic, and how to calculate, we are going to discuss in this today's lecture. So the binary logic deals with variables that take on two discrete values and with operations that assumes logical meaning. Means there should be always a logical meaning between two operations. When we talk about in the arithmetic, we have like addition, subtraction, multiplication, division. So these are the mathematical operations. Now here we are dealing with the logical operations or the logical meanings. The two values, the variables take may be called by different names. Sometimes it is true and false, yes and no, etc. But in case of to make it more convenient, the values of the variable will be either 0 or 1. So we can say that 1 is true and 0 is false. So these are the two values a variable can hold, either a 0 value or a 1 value, as we have discussed in binary numbers. As binary numbers have only two values with the base 2, and the values are either 0 or 1. So again, in the binary logic, the output of any binary logic either will be 1 for true or it will be 0 for the false. When we define the binary logic, it consists of binary variables and logical operations. In mathematics, there are mathematical variables and mathematical operations like addition, subtraction, division, multiplication, percentile. Lots of operations are there in mathematics. Integration, differentiation. The here all operations will be logical. We'll come to that what the term logical means. Now, variables are designated by letters of alphabet such as A, B, C, caps may, X, Y, Z, caps, small, whatever it is, with each variable having two and only two distinct possible values, either 0 or 1. There are three basic logic operations. I think you have studied in first year electronic circuits, and most of you have studied computer science in your 12th 10 plus 2. So you will all very much aware about the logical operation, and the three basic logical operations are AND operation, OR operation, and NOT operation. So by the definition, AND operation is denoted by here X and Y are the two input variables and Z is a output variable. So X dot Y, it is read as X and Y is equals to Z, and the operation is defined as Z equals to 1, means the output of the variable Z will be 1 if and only if X equals to Y equals to 1. Otherwise, the value of the output variable will be 0. That is the definition of the AND operation. Or we can say when both input variables are 1, then the output is true. Otherwise, output is false. Another operation is OR operation, that is denoted by a plus sign. So X plus Y, it is read as X or Y. Again, X and Y here are input variables and Z is the output variable. And we can define the output Z equals to 1 if either sorry X or Y equals to 1, means any one of X or Y is 1, that the output is true, otherwise output is 0. And the last basic operation that is not, it is denoted by x bar or x dash is equals to z. That means it is the complement of the value of x. So z is the complement of x, and it is denoted by if z equals to z is equals to 1 if x is 0, and z equals to 0 if x is 1. So whatever is the value of x, when we take a naught of x, then its value will be complement of x. The binary logic can be represented by the truth table. A truth table is nothing but a table where we have input at the left hand side, x and y. There are two inputs. So again, for the two inputs, the variable is of 2 bit. So we have 4 possible combinations, and these combinations are ranging from 0 to 2 to the power n. 2 to the power n, here n is 2. That means 0 to 2 to the power n is 4. So total 4 combination, and the range will be from 0 to 2 to the power n minus 1, 0 to 3, just like we are doing in a base 2 or base 4 number. So the combinations are 0, 0, 0, 1 that is 1, 1, 0 that is 2, 1, 1 that is 3. So when we go with the definition of x and y, x and y is equals to 1 when both input are 1. So for 0, 0 its value is 0, 0, 1 its value is 0, 1, 0 value is 0, and when x and y both are 1, then the output z equals to x and y will be 1. For the OR gate or OR logic operation, again there are two input variables x and y, and the output z equals to x or y, and it defines that if either of x or y is 1, then the output will be 1. So here we see that for the case of 0, 0, x or y is 0, and in these combination, in the first y is 1, then the output is 1, here x is 1, output is 1, and here both x and y are 1, that means output is 1. Now for the NOT gate, we have only single input x, and the output x z equals to x bar. When x is 0, output is 1. When x is 1, output is 0. So here, as there is only single input, then that means n equals to 1. So 2 raised power 1 is 2. So there are only two possible values of input, either 0 or 1. Here input are of 2 bit. There are 4 distinct combinations, 0, 1, 2, 3. So simply in this manner we can find out how many number of combinations are there and how to write these combinations. Now, logic gates are electronic circuits that responds to two separate voltage levels representing binary variable to logic 1 and logic 0. So these logical operations are done with the help of logic gates, and logic gate is a device and an electronic circuit which takes input in binary in the form of zeros and ones, and which produces an output in the form of 0 and 1. So 1 is a voltage level, say we are working with the 5 volt, then 1 equals to 5 volt. If we are working and 0 is equals to 0 volt, that is ground. The allowable range defines a legal voltage level for a logic 1 and logic 0, logic 1 or logic 0, or first logic and second logic. The intermediate range between allowable range is crossed only during state transition, and transition occurs when the input or the output changes from 0 to 1. So we say there is a negative transition. If the output or input changes from 1 to 0, or 0 to 1, there is a transition when the input is changing. So graphically we can define this like this is in the y-axis we have voltage, in the x-axis. So here we have assumed that from 0 to 1 volt, it will define a range 0. Whenever input or output is between 0 volt and the 1 volt, it will consider it as logic 0. Now, when the output or input value of the voltage is from 3 volt to 4 volt, it will define a logic 1. So this is a range. If I say that the input output is 3.1 or 3.9 or 3.5 volt, so it will read at logic 1. When the input or output is between 0, 0.1, 0.5, zero point 0.9, it will read at logic 0. And the difference between logic 1 and logic 0, this is called a transition period, transition level, and it happens only when a signal comes from 1 to 0 or 0 to 1. Now suppose we have to represent with the signal graph or with the signals. Here are two inputs x and y. We have taken x and y, so there are four possible combinations: 0 0, 0 1, 1 1, and 1 0. So there are only four possible combinations. Then again 0 to 0 0. So for the let us see what will happen when we are ending the operation. X and y, when both input is 0, output is 0. 0 1, output is 0. When both input are 1, then the output will be 1. And again for 0 as 1 0, output is 0. 0 0, output is 0. So whatever was there in the truth table, if we see here of the AND gate, if both input are 1, then the output is 1, otherwise output is 0. So same thing has been shown here with the help of graph. That is known as either in when you learn microprocessor in your 5th or 6th semester, then it is known as timing graph, and as far as the STLD is concerned, it is known as signal graph. So we can represent the basic gates with the help of signal graph. So we stick with our assumptions for the AND operation. When both input are 1, output is 1, and this is called the duration. This is the duration when the transition will occur, and for this particular duration, the output will be 1, otherwise it will change. It is changing from 0 to 1. So here is a transition. Here the output is coming from 1 to 0. Here is a transition. This is called transition phase. Similarly, we can define for the OR gate, the signal graph. Again, these X and Y are the input, and the output of the OR gate is 1 when both input either of X or Y is 1. So when 0 0, output is 0, 0 1, 1, 1 1, 1, 1 0, 1. Again, when the input is 0 0, output will be 0. So here this going from 0 to 1, a transition; coming from 1 to 0, there is another transition. Similarly, for the NOT gate, if I consider that I am noting the X, the output Z is X bar. When input is 1, input is 0, output is 1. Again input is 1, output 0, input 1, output 0, input 0, output 1, input 0, output 1. So the NOT gate is nothing but it is just complementing the bit. If the input is 0, output will be 1. If the input is 1, output will be 0. For AND operation, we have to keep in mind when both inputs are 1, then the output is 1. For the OR operation, when either of the input is 1, then the output is 1. So these are the basic three gates which are used to design as far as up to this knowledge. With the help of these three gates, we can design any circuit or any digital circuit. Now the representation of gates. Here this is an AND gate. This is your symbol X and Y. There are two inputs. Z is output and Z equals to X and Y. For OR gate, it is like this. X and Y are the input. Z is the output. And for NOT gate, it is X and X bar. This bubble denotes the complement. These are the two input gates. We can have multiple logic inputs at the input. In this case, A, B, C. We have three inputs. Then F equals to A and B and C. Many times you need not to write a dot. When there is a no dot, so it is assumed that it is an AND operation. So here it is F equals to A and B and C. We are ANDing three inputs, and in this case again the output will be 1 when all three inputs are 1. When A equals to B equals to C equals to 1, then F will be 1. Otherwise, the value of F will be 0. So again, I have taken an example of 4 input OR gate: A, B, C, D. These are the 4 input variables. G I have defined here an output variable, that G equals to A or B or C or D. I'll write it, we'll write it like, read it like A or B or C or D. Never it is, never it is that A plus B plus C plus D. No, it is A or B or C or D. When we are talking about the logical operation, plus is a OR operation. So again, in this case, we can say that the output G will be 1 if either of the four inputs are 1. So if A is 0, B is 0, C is 0 and D is 1, then the output will be 1. Further, if all inputs are 1, then the output will be 1. Now I'll come to the Boolean algebra and how to manipulate and how to solve, how to design the circuits. That is the basic algebra, as you have written in mathematics, algebra, trigonometry. So here we have, we call it as Boolean algebra, mathematical equations, how to deal with the mathematical expressions. Now when we come to the history of the Boolean algebra, it is given by George Boole in 1815, and in 1847 it was mathematically designed and as a pamphlet called Mathematical Analysis of Logic. And from then onwards, from 1847, we are dealing with the Boolean algebra and we are in the evolution of the digital electronics. Now, these are the identities. I suppose that all of you write it in your copy, because you have to use these particular identities when you are solving the Boolean algebra or the Boolean functions. So let me explain it. Forget about this table. When x is OR by 0, then the output will be x. You can consider it. We have a OR gate. First input is A, another input is 0. So when A is 0, A 0 plus 0 is 0 or 0 is 0. 1 or 0 is 1. So when we OR any input variable with 0, the output will be input variable. Second identity, sometimes it is called postulates. Second identity, if we AND any input variable with 1, then the output will be input variable. So if I AND, if this x can have only two values, either 0 or 1, 0 and 1, 0 and 1 is 0, 1 and 1 is 1. So we say if we OR any input variable with 0, the output is same variable. If we AND any input variable with 1, then the output will be input variable. Next postulate, if we OR x with 1, then the output will be 1, because for the OR operation, if any of the input is 1, then the output is 1. So x may have 0, 0 or 1 is 1. X may be 1, then 1 or 1 is 1. X and 0 is 0, because one input is 0, then the output is 0. For the AND operation, if any of the input is 0, output is 0. Keep writing all these identity in your book when we are going to solve the Boolean expression. These postulates will help you. X or x equals to x. So if I say that the both has the value 0, 0 or 0 is 0, 1 or 1 is 1. So like this. X and x is x. So if x is 0, 0 or 0 and 0 is 0, 1 and 1 is 1. X and x bar equals to 1. That is a very useful property. If x can have two values, 0 and 1, then the x bar is 1 or 0, that is a not. So when we are ORing, 0 or 1 is 1, 1 or 0 is 1. So in any case, if x and x bar, x or x bar is equals to 1, that is the seventh postulate. X and x bar will be 0. So if x has two values 0 and 1, then its complement will be 1 and 0. 0 and 1 is 0, 1 and 0 is 0. X complement, then x naught, then फिर से naught. So 2 times naught, the value will be same. If I say that the x is 0, then 0 bar will be 1 and 1 bar will be 0. So we start with 0 and we find after double complement the same value. Now we have some properties or laws for the Boolean expressions. The first commutative property, x or y equals to y or x. We can change the positions of the input variables. Similarly, for the AND operation, x and y equals to y and x. This is the commutative property. Then associative property, x or y or z equals to x or y or z. So for what we do, we first or y and z in the left hand side, then the result is or by x. In the right hand side, we first or x and y, and the result is or by z. Similarly, the property in AND operation, x and y and z equals to x and y and z. So here we have ended first y and z, then the result is ended with x. In the right hand side, we have x and y, then the result is ended with the value of z. And here each and every variable can have only two values, either 0 or 1. That's why it is called Boolean algebra. Boolean is drawn with the term of binary. A distributive property, x and y or z equals to x and y or x and z. Similarly, here x or y and z is equals to x or y and x or z. This is AND distribution, this is OR distribution. These properties should be remembered when you are solving, and one question in your examination will always be there for the Boolean algebra. Now the de Morgan's theorem says it is very simple and very useful for the implementation of Boolean functions. It says I have x or y. So first I have odd x and y, then I have done is complement. So x or y complement equals to x complement and y complement. Similarly, y or and x whole complement equals to x complement or y complement. And it is very simple to remember. Here it is written x plus y bar whole. Then break the line, change the sign. You just have to, it is x plus y whole bar. Just break the line, then it will get x bar or y bar and change the sign. Or is replaced by and is replaced by or. Again, x and y similarly, x and y whole bar equals to, so we break the line, then we have x bar and y bar and is replaced by or. So here is the proof of the first, x or y whole bar equals to x bar and y bar. So we have x, y, two inputs, then four combinations 0, 0, 0, 1, 1, 0, 1, 1. Then first I have done x or y. X or y is 0, 1, 1, 1. I have complemented x or y bar. So it is complement, 1 is replaced by 0 is replaced by 1 and 1s are replaced by zeros. So for this right hand side, again we have x and y. We have to find out x bar, y bar. X bar is complement of x, y bar is complement of y. Then we have ended 1 and 1 is 1, 1 and 0 is 0, 0 and 1 is 1, 0, 0 and 0 is 0. So you can see these 1, 0, 0, 0 is the output. Again here is 1, 0, 0, 0. So in this way, If you have to prove any property, then you can use the with the help of the truth table. Write down the input variables, find out the terms which you have to prove, and make two tables. You can simply justify the boolean function with the help of the truth table. These properties, or sometimes called laws or theorems, can be used to simplify equations to their simplest form. Now suppose we have an expression f equals to x bar yz plus x bar yz bar plus xz. So here plus is or, and where there is no dot, there is an and. So we can say x bar and yz plus or x bar yz bar or xz. So we have to implement it using the logic gates. So let us first simplify this function. So whatever postulates you have read, we have to apply these postulates into this Boolean function. So here is your expression x bar yz and or x bar yz bar or xz. I have implemented here identity number 14. So what I have done, x bar y is common from the first two term. So it is left with z plus z bar or xz. So x bar y I have taken common from the first two terms. I am left with z plus z bar. And again, we have a property is x plus x bar equals to 1. So I'll apply this property into here. So x bar y and 1 plus xz. So this is identity number 7. You need not to write identity number 7. You just have to simply take common, put the value equals to 1. That's enough. Then again, x and 1 is x. So we are left with x bar y plus xz. So here we have 3 terms, and here I have reduced to 2 terms. Now when we implement it, you will see that how these simplification can reduce the cost of our hardware. So suppose I have to implement this particular Boolean function f equals to x bar yz plus x bar yz bar plus xz. Simply without any simplification, I just have to implement this particular function. So here in this term, we have three inputs x, y, z. So I need here AND के लिए I'll take a 3 input AND gate. Again, this is done by 3 input AND gate, and this is from the 2 input AND gate. And I need a OR gate which can OR both all 3 terms. So when you see this example, this is your x. I have used NOT gate to x bar. This is your first term, comes from here x bar. Now is y comes from here y, z comes from here z. So this here you will get x bar yz. So x bar yz is from the gate number 1. Then again I have x bar. So x bar comes from here, y comes from here, z bar comes from z, and NOT gate, here comes z bar. So this terms gives x bar y z bar, and the last term is x z. So x comes from here, this is z, and this output of this particular gate is xz. Now I need a OR gate to combine these. So I have used 3 input OR gate. So all terms are odd, and I get the value f. So you can see here that we have used 1, 2, 3, 4, 5, 6. So to implement a Boolean function, we need 6 gates, in which 2 are NOT gate, 3 are AND gate, and 1 is OR gate. Now Now, when we implement the reduced gate and the f was reduced with the Boolean algebra, that f was x bar y or xz. So here I implement this is x bar y. So x bar, I have gone through x through a NOT gate. X bar comes from here. Here it is y, the first gate. Second term के लिए x and z. Second gate, there is OR operation. I have used a OR gate. So you can directly see the 1, 2, 3, 4, 5, 6. 6 gates are reduced to the 4 gates. That means the cost and complexity of the circuit. You can see the number of wires, number of connections, number of overlappings between two implementation. In the first implementation, I have directly implemented the Boolean function which was given, and in the next implementation, I have reduced the Boolean function with the help of Boolean algebra. Then I have implemented with the help of gates. So you can directly see the complexity is reduced, number of gates are reduced. As the number of gates and complexity is reduced in the Boolean implementation, that means effectively its cost will be reduced. And when there is less complexity, the circuit will perform faster. So here it is, what is the need of reading or understanding the Boolean algebra? Boolean algebra helps us to reduce the complexity and the cost of the implementation of a hardware. That is the effect, that is the use of Boolean algebra. We can see further some examples. Suppose x plus xy. So I can write it like x and 1 plus xy. Now I take x as common. So 1 or y is 1. So it is reduced to x. So here are two gates, one for AND operation, one for operation. It is directly reduced to x. Another example, you can say x or y, x and y, or x y bar. So again, I take with the property 14x common, then y plus y bar, it is equals to 1. Again, it is x or x bar y. So I can write this x is x or xy. Then x or xy is 1. Then it is x plus y. So this is the way we can reduce the Boolean function, and your answer may differ because which property you are using first and which property later on. The answer may be different, but when you implement or clarify with the help of truth table, then your truth table will be exactly equal, what you are getting the first and what you are getting later on. So this is the way how Boolean algebra is used to simplify the Boolean functions. So we can, all you have to remember these postulates or theorems or laws so that they can be directly implemented when we are reducing the Boolean function. So let us stop today's class here. In the next lecture, we are going to discuss the complements of the function. If any one of you have any doubt, you can contact me on WhatsApp or you can mail me.